everyone, and welcome back. We will be continuing on this time with the remainder theorem. So let me get the backup recording just in case.
Recording in progress.
Hello, everyone, and welcome back. We're continuing on with our course. We are currently working on go. Did have my PDF reader. That would have been a disaster. I'm like, oh, it's gonna be tough to do this lesson then. Okay, so we are continuing on with the MCT 4C course. This is Unit 2, Lesson 7. And so we're going to be looking at the remainder theorem. And so, there we go. And so as a quick reminder of things we're going to be studying today, we'll be having a look at function notation, and that'll actually be our review section. We have the remainder theorem itself. We're going to work with the corresponding statement as well as revisit a topic from the past known as systems of equations. And so as for a success criteria, basically you'll be able to apply the remainder theorem. So understand what it is and then be able to use it and go from there. So one of the few things we need in order to get started is just a review of function notation. And so remember, in this course, typically, depending on the lesson, they might write these things as, say, y is equal to x to the power of 3 plus 4x to the power of 2 plus x minus 2. But the book writes this in terms of function notation instead. So they'll write this as, say, f of x. And functionally, pardon the pun, that means they're just the same thing. So here, given f of x is equal to this cubic function, we're going to determine f of 0. So f of 0 just means wherever you see an x, you just put a 0 there instead and see what the corresponding y value is. So this is going to be 0 to the power of 3 plus 4 times 0 to the power of 2 plus 0 minus, and that's going to be negative 2. Okay. The next one, letter B, will be f of 1. And so this is going to be 1 to the power of 3 plus 4 times 1 to the power of plus 1 minus 2. And again, at this point, I'm going to be using the Desmos scientific calculator today. So if you want to follow along with that, you can pull that out or just have your own calculator. You can always use Desmos to type these things in if you don't want to try to figure these things out manually, which I would encourage. Like, feel free to figure this out as best you can. These questions would only be worth 1 mark. Sorry, 2 marks. 1 mark for inserting the value, 1 mark for the answer. You don't really get marks for in between. And so f of 1 here would be equal to just 4. And so recall f of 1 equals 4 means that this is the ordered pair, 1 comma 4, which is given by x comma f of x. And f of negative 2, done the same way as before, we say that this will be negative 2 to the power plus 4 times negative 2 to the power of 2 plus negative 2 minus 2. And the nice thing about using the Desmos calculator, you can just swap out the value you care about and just sub in the number instead. So instead of 1 here, I'm just going to type in negative 2. And we can see here, we also get a solution of 4. Okay, so f of 2 both happen to equal 4 by coincidence. Okay, so that's the notation we're going to be using for this particular lesson. Okay, and so we're going to explore the remainder theorem, and the best way to explore this is actually through the lens of vision. And we want to motivate the reason why we want to bother with remainder theorem to begin with. And so given a function, say f of x is equal to x to the power of 3 plus 4x to the power of 2 plus x minus 2, we're going to find the remainder when our function is divided by x minus 1. Now note, again, the last 2 videos we spent time working on this, but again, I'll show all the steps for this. So we want to take our x minus 1 and divide it into x to the power of 3 plus 4x to the power of 2 plus x minus 2. And so we ask ourselves the question, how many times, and essentially we're always thinking about this x to the power, this x term in front of the binomial. And we want to see how many times x goes into x cubed. Or another way of thinking about that is, what is x to the power of 3 divided by x? And so that's going to be x squared. So we're going to put x squared up here, and on this line, we will place x to the power of 2 multiplied by x minus 1. So x to the power of 2 times x will be x to the power of 3. X to the power of 2 times negative 1 will be negative x squared. And so we minus off these quantities. 4 minus negative 1 is going to be 5 of the x squared variety. And we bring down the next term. Plus x. Now, here's the question. How many times does x go into 5x squared? Or an alternative way to think about that is to say, what is 5x to the power of 2 divided by x, which means it's just going to be 5x. And so that's a 5x. So we'll put a plus sign here. And down here, we're going to write 5x multiplied by x minus 1. So 5x times x is going to be 5x squared. 5x times negative 1 will be negative 5x. And we'll minus these off. By design, we know we're doing this right if we take, because if we notice 5x squared minus 5x squared is 0. So that's going to be done well. So x minus negative 5 is going to be 6 of the x variety. And we bring down this negative 2. On the last line, we ask ourselves the question, how many times does x go into 6x? Or another way to think about this is if we take 6x divided by x, that's going to be 6. And so on this last line, we're going to write positive 6. And so it'll be positive 6 multiplied by x minus 1. So that's going to give us 6x minus 6. And we're going to minus off these quantities. So we know 6x minus 6x will be 0. Negative 2 minus negative 6 will be 4. And x doesn't evenly go into 4. So we would say that this thing has a remainder of 4. Okay, so why did we do that? Well, if you notice here, we got a remainder of 4. But above here, we found that f of 1 happened to be 4. Now, the next question you might be asking is that coincidence? No, that's actually intentional. In fact, that's always true. So note that when we divided f of x, by f of x, I mean this cubic function, by x minus 1 and achieved a remainder of 4, this is the same as when f of x is evaluated for f of 1. And so this leads to what we call the remainder theorem. And the textbook has this as well. When a polynomial f of x is divided by x minus b, then the remainder is f of b. Okay, so if I want to know the remainder when this thing is divided by x minus 1, I just type in f of 1. And I'll show you how I know that it's 1 and not negative 1. And so we're going to apply the remainder theorem to these examples. And so when f of x is equal to x to the power of 3 minus 5x to the power of 2 plus 10x minus 15, we're going to determine the remainder when f of x is divided by all of these things. Okay, so when we want to see what value we're supposed to check, we just set x plus 1 equals 0. And so x will be equal to negative 1. And that's the value we're going to check then. So what we're going to be typing into our calculator or using mental computing power, whatever makes you happy, f of -1 will be equal to -1 to the power of 3 minus 5 times -1 to the power of 2 plus 10 times -2 minus 15. I'll be using a calculator. This is these are the kind of calculations I'm very likely to get wrong if I just try to figure these out off the top of my head. But again, I'm using just the Desmos scientific calculator for us today. So, and we could just type this in. You can also evaluate this if you so choose, term by term. But at any rate, when I type in f of -1, that is equal to -31. So it's worth noting that if you wanted to, you could also graph this using the Desmos graphing calculator, and this would correspond to the point -1 comma, -1 comma -31. So that point would be on the graph. Okay. So that's going to be the concept for these next three. At this point, if you're watching this on YouTube in the future, this would be a good time for you to go ahead and pause the video and try this out. Okay, let's continue on. So we've got x minus 3. So we're just going to set x minus 3 equal to 0, plus 3 on both sides. So x will be equal to 3. And so what we're going to type in will be f of 3 is equal to 3 to the power of 3 minus 5 times 3 to the power of 2 plus 10 times 3 minus 15. And so I can just edit the entries on my calculator here. I can swap all of the -1s for 3. And I can see that if I take 3 to the power of 3 minus 5 times 3 to the power of 2 plus 10 times 3 minus 15, I get as a solution that f of 3 is equal to -3. Okay, so far so good. You might be asking, are these some key questions? Yes, this is the majority of the key questions, is testing information like this, as well as being able to use some properties of this. And again, we're going to cover some properties later on. But for now, again, we just practice the concept. Okay, what about x plus 5? Well, we're just going to set x plus 5 equal to 0. So we're going to test the value of -5. And so f of -5 will be equal to -5 to the power of 3 minus 5 times -5 to the power of 2 plus 10 times -5 minus 15. Okay, and so f of -5 will be equal to, and again, I'm just going to edit the entries on my calculator here. So in place of 3, I'm going to swap out -5 everywhere. And so I get a large number. So this is going to give us -315. You might be thinking, does that make sense? Yeah, -5 to the power of 3 is -125. And then we actually have another -5 right -5 to the power of 3 beside it. So it's already at -250. So this number does make sense. Again, to be clear, this would correspond to the point -5 comma -315 on the graph. And this point would correspond to the point 3 comma -3 on the graph. The lesson doesn't talk about the connection between the remainder theorem and the graph of the polynomial, but for our purposes, that's why I want to make it just a quick aside to that to confirm that those are directly related to each other. Okay. Lastly, but not leastly, suppose we have x minus 2. So again, follow the exact same formula as before. Set x minus 2 equal to 0. So x must be equal to 2. And so to the power of 3 minus 5 times 2 to the power of 2 plus 10 times 2 minus 15. Okay, I just go back up to check to make sure we're doing these things correctly, and we are. And so f of 2 will be equal to, And again, I'm just on my calculator going to swap out -5 for 2. And I get as an answer -7. Okay. And for clarity purposes, this does correspond to the point 2 comma -7 on the graph. Okay. So this is the remainder theorem. This is the basics of how these things work. Okay. So this is already like a good chunk of the lesson. So there's a lot of practice. You'll be able to try these out. But now let's try out some, I want to confirm some of these are correct. So we're going to verify our answer for letter D using long division. So we should be getting an answer of -7 at the end. And if we didn't, that means we likely typed something into the calculator wrong. So let's have a look. Okay, so we're going to take our x minus 2 and we're going to insert it into, or divide it into, I should say, x cubed minus 5x squared plus 10x minus 15. And so first thing we want to ask ourselves, I think we want to be consistent, use green. How many times does x go into x cubed? And the answer to that question is x cubed divided by x is x squared. And so we'll line up our x squared above. And on this line, we take our x squared and multiply it by x minus 2. So x to the power of 2 times x will be x to the power of 3. X to the power of 2 times -2 will be -2x to the power of 2. And again, we want to go ahead and subtract these quantities. So x to the power of 3 minus x to the power of 3 is 0. -5 minus -2 will be -3 of the x squared variety. And then we bring down that 10x. You might be thinking again as a review, this feels like it's just long division with polynomials. It is, albeit it has artificial difficulty in terms of it looks much more complicated, but it's the exact same algorithm, albeit with variables instead. Okay. So we must ask ourselves the question now, how many times does x go into -3x squared? Or the equivalently, we could say, what is -3x squared divided by x? And that's going to be -3x. And so we write up here -3x for our quotient. And on this line, we take our -3x, multiply it by x minus 2. So -3x times x will be -3x squared. -3x times -2 will be positive 6x. And then again, we want to go ahead and subtract off that quantity. So -3x minus -3x, both squared, is going to give us 0. 10 minus 6 will give us 4x. And then we bring down this -15. Okay. So last thing we'd like to do is ask ourselves, how many times does x go into 4x? Or we could say 4x divided by x will be equal to 4. And so that's just a regular 4, so we'll plus 4 up. And on this line, not quite even, that's close enough. We take 4 multiplied by x minus 2. Okay, so 4 times x is 4x, times -2 is -8. And we want to subtract off these quantities. So 4x minus 4x is 0. -15 minus -8 is the same thing as 7. And so this thing has a remainder of 7, which, if you notice on the left here, oh, sorry, -7. I was like, oh, no, it's different. No, we're good. -15 plus 8 is going to give us a -7 here, which is what we got from our previous answer from above. So you can use the remainder theorem to check your long division, or you can use long division to check the remainder theorem. It's just important to understand that both of those are working, just be comfortable working with those. So there is an extension of the remainder theorem. So in general, when a polynomial f of x is divided by ax minus b, then the remainder will be f of b over a. And so say for an example given, we want to take f of x and divide it by, say, 3x plus 4. We would set 3x plus 4 equal to 0 minus 4. So that'd be 3x equals negative 4. And so x would be equal to negative 4 thirds. So then if you wanted the remainder, you would check f of negative 4 thirds. Okay, a couple of the key questions ask you to do this, and the book doesn't explain this part at all. So that's why I wanted to provide a little section here for you as well. So let's have a look. And so I've got 3 examples for us, and we're going to rely pretty heavily on this calculator because these are way too hard for me to try to figure out. So we're going to apply the remainder theorem. So when f of x is equal to 3x to the power of 3 plus x squared minus 4x plus 6, we're going to determine the remainder when f of x is divided by each of the following. And I've got 3 examples for us here. Okay, so first thing we do is we set 2x minus 1 equal to 0. So that means 2x is equal to positive 1, and x will be equal to 1/2. And so what we want to check then will be f of 1/2. And again, I like using the Desmos calculator because it even has a fraction button for us if we're so inclined, because sometimes classes do care about that. Otherwise, decimals are normally fine. So this will be 3 times 1/2 cubed plus 1/2 to the power of 2 minus 4 times 1/2 plus 6. And so f of 1/2 will be equal to what? Well, let's go ahead and type this in. So this will be 3 bracket 1 over 2. And again, this is useful if you're following along. Do practice typing this in as well, just to make sure things are going well. 1 divided by 2. And this is to the power of 2 minus 4 times 1 divided by 2, close the bracket, and then we plus 6 at the end. And so we get as an answer 4.625, or if you prefer, you can use this fraction button here, and it'll make this 37 over 8. Either answer is okay. We're not too picky as to what the answer is, but if you use the Desmos calculator, you can easily get both solutions. Okay, so we're going to apply the same concept to examples B and C. So at this point, this would be a good time for you to pause the video and try this out for yourself if you're watching on YouTube, and then we'll go from there. Okay, so 4x plus 5, we're going to set 4x plus 5 equal to 0. So 4x equals negative 5. And so x is equal to negative 5 over 4. And so what we would like to check is f of negative 5/4. So this will be equal to 3 times negative 5 over 4 to the power of 3 plus negative 5 over 4 to the power of 2 minus 4 times negative 5 over 4 plus 6. Again, this is too much heavy lifting for me, so I'm just going to substitute these values into my calculator. So wherever I see the 1/2, I'm going to put negative 5 over 4 instead. And so we get as an answer that f of negative 5/4 is equal to 429 over 64, otherwise known as some decimal. Looks like 6.703125. So there it is for you. Okay, lastly but not leastly, we have 4x minus 1. And so again, we can follow the exact same steps. we set 4x minus 1 equal to 0. So 4x will be equal to 1, and x will be equal to 1/4. And so when evaluating this, f of 1/4 or 4 equal to 3 times 1/4 to the power of 3 plus sign 1/4 to the power of 2 minus 4 times 1/4 and then plus a 6 at the end. Oh, minus 5. Okay, I was making sure that I typed it in wrong, but no, we're okay. Okay, so I'm going to swap out the -5 for a 1/4. And again, I'm using the Desmos calculator. If you just type into Google, let's bring up my screen for a second, just Desmos scientific calculator, it'll be there for you. Okay, so that's what I'm using for the course. And we get as a solution that f of 1/4 will be 327 over 64, or 9375. Didn't specify how many decimals it wanted, so we'll just take the whole thing, or you can just leave it as a fraction if you're uncertain. Okay. So we had to look at the remainder theorem when we divided by a simple binomial, such as x plus or minus some number. And now we had to look at binomials where we were dividing by a binomial of the form ax plus b, so like 7x minus 3 and so forth. And you should be able to most of the questions now relate, find the remainder style. So this is what we're doing. So keep in mind, all of these determine a remainder. So this 37 over 8 is the remainder. This 6.7, whatever number, is the remainder. And you can use either the decimal or the fraction form if the question doesn't describe what to use. Okay, let's continue on. Division by x is a weird question. Determine the remainder when each polynomial is divided by x. So what do? Well, keep in mind, we're trying to take a function f of x and we divide it by x. This looks pretty unusual, but remember, what did we try to do when we said, say, f of x was divided by x minus 4? Well, we set x minus 4 equal to 0. So then x is equal to 4. And so I bring the step up because we do the exact same thing here. Now it's just dividing by x. So we're going to set x equal to 0. That's it. So for all of these, we're just going to evaluate f of 0. So we're looking at x. So we want to know the remainder when x to the power of 2 plus 5x is divided by x. So all of set x equal to 0. And we're going to test out the long division at the bottom to make sure things look reasonable. This one I don't need a calculator for, but we'll have it here anyways. This will be 0 to the power of 2 plus 5 times 0, which is 0. For letter B, we're having a look at f of 0. So this will be f of 0, x to the power of 3 minus 2x plus 8. So we're going to write down 0 to the power of 3 minus 2 times 0 plus 8. So that's just going to be 8. You might notice a pattern with these fairly quickly. If you're dividing by x, that means you're going to end up with a constant at the end. So without looking, I know that my answer for this is going to be 7, but let's confirm this is the case. So we're having a look at f of 0, and the cubic in question is negative x to the power of 3 minus 5x squared plus 2x plus 7. So this will be negative 0 to the power of 3 minus 5 times 0 squared plus 2 times 0 plus 7. And sure enough, that's going to give us 7. So we've now had to look at division by binomials, and we've also had to look at division by just x, a monomial. Okay. So the question you might be interested is, well, I'd like to figure this out using long division when we're trying to divide by x. We can do that, not a problem. So we're going to take x and divide it into x squared plus 5x. So what does this look like? Well, we still answer the first question. How many times does x go into x squared? And so that's the same thing as saying, sorry, I like to color code these. We take x to the power of 2 over x, which is just x. So that's going to go just up here. And so on this line, we write x times x, which is going to be x squared. And already you could see how this works. All that happens is that we now don't have to worry about, there's no second term here. We just work with one term at a time. So x squared minus x squared is 0. So then we just bring down this 5x. And so then we ask ourselves, how many times does x go into 5x? So if we take 5x and divide it by x, that's just going to be 5. And so we ran out of space up here, so let's continue this on. We will write our plus 5. On this line, we're going to write 5 multiplied by x, otherwise known as 5x. Subtract it with a remainder of 0, which is the answer we got from above, where f of 0 happened to give us 0. So you can verify this using long division. And in fact, dividing by x is actually way less work than trying to divide by a normal binomial. Okay. Let's continue on. So this is another large set of questions that we had to look at on the lesson of last time. We had to look at something called undetermined coefficients. And that method was a lot of work. While interesting, it seemed like a lot of work. The remainder theorem is actually a lot easier to solve those kinds of questions. And so when the polynomial x power 3 plus kx squared plus x minus 2 is divided by x minus 2, the remainder is negative 8. So we're going to determine the value of k. And so remember, we're going to set x minus 2 equal to 0. So that means here x will be equal to 2. And so f of 2 is going to be equal to 2 to the power of 3 plus k times 2 to the power of 2 plus 2 minus 2. But what's this all supposed to equal? Well, we saw earlier that the remainder was 8. Sorry, was it negative 8? So this is going to be equal to negative 8. And we can actually solve this equation now. So 2 to the power of 3 is going to give us 8. 2 to the power of 2 is 4. 4 times k is just 4k. And then we have plus 2 minus 2. This is supposed to equal 0. So 8 plus 2 is 10. 10 minus 2 is 8. And so we end up with 4k. Oh, I saw the mistake. Let me go up there. I should say that 8 plus 4k plus 2 minus 2 is equal to negative 8. So 8 plus 2 is 10. 10 minus 2 is 8. So 4k plus 8 will be equal to negative 8. Subtract 8 from both sides. 4k will be equal to negative 16. And consequently, we know that k must be equal to negative 16 over 4, which is just negative 4. So therefore, we can conclude that k must be equal to negative 4 in order for this to make sense. And this method is much quicker to evaluate than when we were trying to use the method of undetermined coefficients. But again, that method is quite useful for a lot of future maths as well, and has good properties with respect to understanding. Okay. So letter B, when the polynomial kx to the power of 3 minus 2x squared plus 7x minus 4 is divided by x plus 4, the remainder is negative 17. So we're going to determine the value of k. Okay. And so here we're going to set equals 0. So x is equal to negative 1. And so we know that if f of x, or I should say f of negative 1, will be equal to k times negative 1 to the power of 3 minus 2 times negative 1 to the power of 2 plus 7 times negative 1 minus 4. And this must all be equal to the remainder, which was negative 17. Okay, negative 1 to the power of 3 is going to be negative 1 with a k, so this will be negative k. Okay, so here we've got negative 1 to the power of 2, which is 1. 1 times negative 2 is negative 2. 7 times negative 1 is negative 7. Then we minus off the 4, which will give us negative 17. So negative 2 minus 7 is negative 11. Negative 2 minus 7 is negative 9. Negative 9 minus 4, negative 13. So this will be negative k minus 13 will be equal to negative 17, plus 13 on both sides. So this will be negative k is equal to negative 4. And then we can flip the signs here. So then consequently, k will be equal to 4. And so we can conclude that k in this instance will just be equal to 4. And at this point, you can go ahead and take this value and substitute it back into, say, in place of k, and verify that this is the case if you want to confirm your answer is correct. Because the nice thing about this particular unit or this lesson is that all of your answers can be confirmed. Because you can confirm this by now checking the case where k equals 4 or checking this via long division. Both of those will be acceptable. Okay. Let's check out the next one. We have when the polynomial x to the power of 4 plus kx to the power of 3 minus 7x squared plus 4x minus 5 is divided by x plus 4, the remainder is 5, and we need to determine the value of k. Okay, first thing, we set. And at this point, again, make sure to pause the video if you'd like to try this out for yourself. Okay, so we're going to set x plus 4 equals 0. So that means x equals negative 4. And so f of negative 4 will be equal to, these are big numbers, but we're going to figure it out. Negative 4 to the power of 4 plus k times negative 4 to the power of 3 minus 7 times negative 4 to the power of 2 plus 4 times negative 4 minus 5. Let's gotta write this out neater. It's a little not, I can write a bit neater than that. Minus 5. And this is supposed to all be equal to the remainder, which is negative 5. Okay, negative 4 to the power of 4 is the same thing as 16 times 16. So that's going to be 256. Negative 4 to the power of 3 is going to be minus 64 of the k variety. 4 to the power of 2 is 16. 16 times 7 is going to be 112 of the negative variety. 4 times negative 4 is negative 16. Minus 5 is equal to negative 5. So now we got to collect the constants. So if we take 256 minus 112 minus 16 minus 5, that's going to give us 123. So we're going to have here negative 64k plus sign 123 will be equal to negative 5 minus 123 from both sides. So we're going to end up with negative 64k is equal to negative 128. And if you take 128 divided by 64, you actually get a nice number of the negative variety. So you end up with k equals 2. So therefore, we can say k is equal to just 2. This was a support question. So often when I go through these kind of questions, most of the time I'll either take some of the examples from the course, go over them, a support question, or I'll pull in my own examples, some combination of all of them. But all of what I'm going through will be helpful for you with respect to understanding the material. Okay. Last question. It gets a whole page because I anticipate doing another example. And so we're having a look at a system of equations and the remainder theorem. And so I should preface this by stating that if we want to solve this kind of question is the same thing as solving, say, n minus n is equal to, say, 5, and m plus n is equal to 1. So the equation above with polynomials is actually going to reduce down to this one down here. So this method to solve this, we're going to use something called elimination. And to do this, if you're having a look at equations 1 and 2, we want to either add or subtract, and we'll put in brackets, potentially, oh, let me spell that again, potentially, a multiple of one equation to the other. So what do I mean by that? Well, right now, if I were to add these two equations together, m plus m is 2m, negative n plus negative m is 0. 5 plus 1 is 6. So if I want to solve 2m is equal to 6, that means m had to be 3. And so then afterwards, I can insert m equals 3 into one of my equations. Let's say equation 1. So this will be 3 minus n is equal to 5, minus 3 from both sides. Negative n will be equal to 2, and then n will be equal to negative 2. So what I'm saying is, for a system of equations, this is a set of ordered pairs that satisfies both solutions. And so what I'm claiming then is that m comma n will be equal to 3 comma negative 2. And we can also check our answer to make sure things went well. So if I want to check equation 2, if I have, say, m plus n equals 1, then if I have 3 plus negative 2, I should equal 1. And 3 plus negative 2 is 1. So 1 equals 1. So therefore, our left side equals our right side. So this is what I mean by you have to use a system of equations. So there are two values such that when substituted into these equations, it'll result in both the left and right side being equal to each other and satisfy both solutions. This happens to be what we call an intersection, and this is a topic that you may have or may not have studied in the distant past. And so you need to know this for one of the questions on the assignment for the lesson, which is why we're covering it here. So this is the simple example of just m minus n equals 5 and m plus n equals 1. So what are we going to look at? So we're going to look at systems of equations in the remainder theorem. And remember, what I told you is that it's going to look like this thing that we just did at the bottom. Okay. So when 2x cubed minus mx squared plus nx is minus 2 is divided by x plus 1, the remainder is negative 12. And when divided by x minus 2, the remainder is 0. So to determine the values of m and n. So there are some certain values for m and n, such that when they're inserted into this equation and evaluated for those remainders, it'll be balanced. So we can see an x plus 1, so that'll be a negative 1. We have an x minus 2, so that'll be 2. So just recall, or what we're going to stipulate, is that for equation 1, f of negative 1 will be equal to negative 12. And for the second equation, what we're stating is f of 2 will be equal to 0. So have a look and see what this looks like. So for equation 1, so we're having a look at f of negative 1. That's going to be 2 times negative 1 cubed minus m times negative 1 squared plus n times negative 1 minus 2, and this is supposed to equal negative 12. So cleaning this up, we could just write this as negative 12 over here. So negative 1 to the power of 3 is negative 1 times 2, so it'll be negative 1, minus m times negative 1 to the power of 2 is just minus m. N times negative 1 is negative n. Then we just tack on a minus 2. Let's clean up the terms. So we have negative 12 is equal to negative 1 minus 2 is going to be negative 3 minus m minus n. And then we plus 3 to both sides. So our first equation is that negative 9 is going to be equal to negative m minus n. Okay. By a similar token, we're now going to show that f of 2 is 0. And so we're going to say f of 2 will be equal to 2 times 2 to the power of 3 minus m times 2 to the power of 2 plus n times 2 minus 2. And this is supposed to equal 0. So 0, 2 times 2 to the power of 3 is just going to be 16, minus 2 squared is 4, so it'll be minus 4m. N times 2 is 2n minus 2. 16 minus 2 is good. So this will be 0 is equal to 14 minus 4m plus 2n. And then move the plus 14 over. And so we have here negative 14 is equal to negative 4m plus 2n. Now, if you notice, all of these happen to be a multiple of 2. Right? I can take negative 14 and divide it by 2, negative 4m divided by 2, and positive 2m and divide it by 2. So I'm going to multiply both sides by 1/2. So this will be negative 14 by negative 14. I, of course, meant negative 14 times 1/2, which is negative 7, is equal to negative 2m plus n. And this will be my equation number 2. And so now if you notice here, my equation 1 will be negative 9 is equal to m minus n. And for equation 2, I have here, and I'll color code this one, negative 7 is equal to negative 2m plus n. So in this case, if you notice here, if I have to add these equations together, I will eliminate those n's. So negative 9 minus 7 is going to give us negative 16. M plus negative 2m is going to give us negative m. So that means m is going to be equal to 16. And so if I take m equals 16 and insert it into, say, equation 2, I did equation 2 because I got a plus m, so it's going to be a bit easier. Then we could say negative 7 is equal to negative 2 times 16 plus n. Negative 2 times 16 is going to be negative 32 plus n, plus 32 on both sides. So n is equal to 25. And then we can conclude that m comma n is equal to 16 comma 25. Okay. So it's a lot more work for this one because the difficulty does not lie with applying the remainder theorem. The difficulty applies with actually solving the system of equations. But between the example one we did at the bottom and this one we did here, hopefully you'll be okay. Now, feel free to email me if you have questions about this. I can give you additional examples. But when I mentioned that you want to apply multiples of these things, note that if a multiple of this was multiplying by 1/2, which actually halved all the values. There was nothing, I just did that because it made it easier, but I also could have taken this equation and say times it by 3 or times it by 4 or what have you, in order to make it such that when I added or subtracted the two systems equations, it resulted in the same value. Okay, so for now, I think that's a good place to stop for the day. We're going to finish 4 minutes early, so I'm going to give you back some time from the past. Thank you all for following along, and if you have any questions, feel free to reach out to me. Tomorrow, we're going to look at a consequence of the remainder theorem called the factor theorem, which we alluded to before, but we're going to be studying in depth. So goodbye for now, and I'll see all of you next time.